In this video, we're going to derive the push-forward or Jacobian vector product rule for matrix multiplication. This operation can also be seen as a function that takes two matrices, let's call them A and matrix B, and then performs the matrix multiplication A times B. Let's call the output of that operation matrix C. Let's assign some dimensionality to the matrices. So let A be a matrix from an M by N dimensional space. Then B shall be a matrix from an N by O dimensional space. And then, according to the properties of the matrix multiplication, the innermost dimensions will cancel out, and the result therefore has to be a matrix that is of shape M by O. Our task for the push forward or JVP rule is to forward propagate. So we have to forward propagate tangent information, and tangent information is given in terms of tangents on the input. This is an A tangent, which has the same dimension as the original input A. So it is an M by N dimensional matrix, as well as a tangent on B, which shall be an N by O dimensional matrix. And then we have to propagate this to the tangent on the output, which will be C dot, and it has the same dimension, which will be M by O. And mathematically, we can loosely write down the task in the form of that we get the tangent on the output, so matrix C dot, equal to dF by dA, so derive the output of F with respect to A, and then contract it with the tangent on A. So in a sense, if we look at F in terms of its output, which will be a matrix, and here we are deriving a matrix with respect to a matrix, then we get a rank 4 tensor, which we are then double contracting with a matrix, and that will then yield a matrix. It's a little bit informally here in symbolic notation. And then we add the same but with B, so dF by dB contracted with B dot. And I say loosely because working with these higher dimensional tensors in symbolic notation is always a little bit ambiguous. Therefore, let's change to index notation. And before we write down the push forward rule in index notation, let's again note down the forward rule, which is just the primal computation. So this one here. And we know that we get C, and let's introduce some indices. Let's say I, K. So we get the ith row kth column of C as the product of Aij with Bjk. And here we are assuming the Einstein summation convention by the contraction of indices that appear twice in a multiplication. So here we will have the Einstein summation convention. If you don't want to use that, you could also just use a summation here and sum over all the entries in J. And essentially, this is what a matrix product is doing. And also as a consequence, the output matrix will then have the indices that are left untouched, so AI and BK. Similarly, we can write down the push forward rule. So the push forward rule. So we will get the dot on CIK to be the derivative of CIK. And here I'm using the output, so I'm saying that the function is equivalent to its output. So the derivative of CIK with respect to, and now let's introduce some new indices. Let's for instance use AMN and then multiply this with A dot MN. And here in index notation, I think it becomes clear that we have the contraction between the tangent and the denominator in this differential form. So we derive a function with respect to its input and then contract with the tangent information on that input. Similarly, we will get it for the second argument. So this will be dCik with respect to BMN using the same indices here, and then contracted with the tangent on B index MN. So in order to fully write down the push forward rule, we have to evaluate these two derivatives here. Let's give this here a 1 and a 2. Let's start with 1 and do the derivative of Cik with respect to AMN. For this, let us go back up and look at the forward rule. So here we take the derivative with respect to AMN. So essentially our derivative operator will propagate, and this is equivalent to DAIJ with respect to AMN multiplied with BJK, because BJK does not have a dependency on A. So here essentially we will then have a derivative of a matrix with respect to a matrix. And whenever this appears in index notation, the result or the tool we use is the Kronecker delta. And that is because the result of this derivative will only be 1 if indices match identically. So if I is equal to m and j is equal to n, then we will get a 1. Otherwise we will get a 0. And this is encoded by using multiple Kronecker deltas. So here we will get delta im delta jn times bjk. And a similar story holds true for the second derivative we have to evaluate. So the derivative of Cik with respect to bmn. And here the a will be untouched. So we will have aij and then multiply it with the derivative of bjk with respect to bmn. So derivative of bjk with respect to bmn. And then we will get similarly Kronecker deltas, slightly different here. So we will get a delta jm and a delta kn. Okay, let's plug this back in. So let's have again the tangent on C, index ik, is given according to delta im delta jn bjk and then tangent amn plus aij delta jm delta kn multiplied with the tangent bmn. And then we will resolve the Kronecker deltas and make an index change. So we can either do an index change from I to m or from m to I, but we have to be careful that we match the indices in the summands or also on the left-hand side. So it is reasonable to change to I and j. So we will change the indices here from m to I and from n to j. So we will get bjk, tangent a, and then index ij plus, and here we will make a similar change, and for this we will do that on the tangent on b. So we have aij and then change m to j, so b dot j, and then change n to k, so a k here. And let me just swap the order here so that we have the indices over which we contract in a similar fashion as in the original matrix multiplication. So we have a dot index ij times bjk plus aij times tangent bjk. And this allows us now to go back to index notation. So back to, of course, symbolic notation. We were in index notation. And then we get that the matrix dot on C is equal to, and here we see these are essentially just matrix multiplications. So we will have matrix A tangent, matrix multiplied with B, plus matrix A, matrix multiplied with the tangent on B. And in a sense, what we got is really similar to how you would handle the push-forward rule with scalar multiplication. Okay, in total, we can then write the full push-forward rule, so the full push-forward rule, and that one is the forward rule on the function f, and we defined f to be a matrix multiplication, which had the primal inputs a and b, as well as the tangent inputs a dot and b dot, and the result shall be first the primal computation, which will be the original matrix product a times b, which results in the matrix C, and then we will have the tangent propagation, which will be according to what we derived here, so it will be a dot times b plus a times b dot, and that shall be it exactly. So this is then C dot. And This is the push-forward rule for matrix-matrix multiplication. Again, look at the similarities between the scalar case and here in the tensor case. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There's more awesome content like this. Here you will now see similar videos, and I hope to see you in one of the next videos.